this problem, and we can obtain x, position vector of the point of intersection, from the data, which was P, B, N, and Q. P and B determining the line, N and Q determining the But note that, now the picture kind of suggests some small finite part of the plane. So I've drawn it as a square, but really, this problem that we've looked at, this deals with the infinite extended plane. Determined by N and Q. But that doesn't get us all the way to solving our problem for figuring out which polygonal face of one of the buildings is hit, because buildings in a real environment don't have infinite extended, aren't of infinite extent. They're bounded polygons of a certain size. So we need further to solve the point in polygon problem. I.e., given a polygon, in the plane, is x inside the polygon or x outside the polygon? So let's call this. So let's call the plane P, capital P. Careful not to distinguish it from vector little p. And let's call this polygon. Let's just for the moment call it R. So the point in polygon. So is x inside R or outside? So in order to discuss this, we'll just discuss this first within 2 dimensions. Okay? Now, we need to be able to do it inside a 3-dimensional environment. But for the moment, let's just simplify matters and let's just look at the mathematics that's involved in solving the problem in 2 dimensions. And then then we'll discuss how we take the kind of maybe slightly harder problem of dealing with a polygon or a plane in 3 dimensions and a line moving through the 3 dimensions, how we reduce it to the 2-dimensional. So we'll first consider the problem in 2D. So we'll take the polygon R defined by its list of vertices. Here's R, and it's got vertex 1, vertex 2, vertex 3, and so on. So we'll take this to be an oriented, a list of vertices which takes you around the boundary of the polygon. So it's an ordered list of vertex. Vertex 1 followed by vertex 2, followed by vertex 3, all the way around. we've got a polygon R and a point X. Point X over here is given by a position vector label X. Okay, so we think of everything defined as vectors. So the vector X, the position of the point, we can think of coordinates as x0, y0, say. And vector V you could think of as coordinates x1, y1, x2, y2, etc. Okay, we might need to refer to the individual coordinates. So what we want is some procedure that, given all these components, x0, y0, x1, y1, x2, y2, etc., given all those components, it's just going to answer inside or outside. It tells you whether this x is in there or outside. And the fact that the problem can get complicated because polygons can be complicated. Polygons can be awkward. And we don't tend to find too many of these awkward polygons in a typical virtual environment. You know, that's a kind of a nice, well-behaved polygon, but there's nothing to stop us I mean, you know, that's quite an awkward polygon. It's not immediately obvious if I specify a point somewhere here, whether it's inside the polygon or outside, because these regions here can be a bit. It's clear that the inside here, if you shade it and follow it around. In fact, I even confused myself when I was drawing it. So it narrows a bit there. There's a polygon, so like these points in this region here are outside the polygon. Yeah? These points are inside the polygon. There's an inner bit here surrounded by an outer bit, but then, you know, here's an inner bit, and then there's another outer bit on the outside. Okay? As an aside, it's very much a non-trivial problem in topology. So here we're only dealing with polygons, so curves made up of a finite number of straight line pieces. There's a more general problem of having curves. Now, you've heard me talking in maths methods about simple closed curves. Okay, here's a non-trivial simple closed curve. Okay, it's gone all over the place. Now, it's kind of intuitively obvious that, or it seems to be intuitively obvious that a simple closed curve splits the plane up into two parts. There's a part outside, so this bit out here is certainly outside the plane, outside the curve. And somewhere in here, there's a bit inside the curve. But you can kind of see where some of the complication arises. Like, is this bit inside or outside the curve? You can't immediately answer it. You kind of have to start out here and see if you can get to this location here where my finger is. Well, we have to come around this side and come in here and see if we can get there, but I think we can't. So I think this finger actually is inside the curve. But this finger is outside the curve. But it's not immediately obvious. So in topology, there's something called the Jordan curve theorem. It took quite a while. It was only, it might even have been, it may have been a 20th century result, which we'd regard as rather late in the development of mathematics, perhaps. So the Jordan curve theorem says every simple closed curve splits the plane, splits R2 into two regions. An outside and an inside. The difficulty is caused by maybe the possibility that some extremely complicated curve like this could maybe split it up into three regions. Maybe there's only one. Maybe the inside is the same as the outside. So it was relatively late that mathematicians were able to straighten things out and figure out a clear, rigorous argument that established that there was only two regions. Okay, but that's kind of an aside. Those, we're not going to be concerned with the substance there. But that does show you the awkwardness posed by awkward shaped regions like this. So now this point in polygon problem can be solved in a number of ways. So the first way I'll show you isn't applicable to all curves, all polygons. It's a simple case. So this is the simple case of convex regions, convex polygons. So the definition of what convex means for us here, for this purpose, convex means for every 2 points, let's call them x1 and x2 within the polygon R, the straight line segment joining x1 and x2 straight line segment joining x1 and x2 also is contained in R. So this kind of region is convex. Think of any 2 points within this region, any 2 points inside this polygon. The straight line between them is always also included in the polygon. Whereas this kind of region, this kind of polygon is not convex. And this isn't convex because I can choose a point x1 up here and a point x2 down here. The straight line between those is not all of it within the polygon. Some of it goes outside the polygon. So this is not convex, but this is convex. This appears to be the way I think this is a straight line. Maybe this little inward wobble here actually makes it non-convex, but these are actually nice straight line pieces. And it's convex. Okay, so our first method is just going to apply to convex regions. And we simplify it even still by splitting a convex polygon up into a union of triangles. By taking a point in the center, and we can take the centroid, joining the centroid to each of the vertices, we'll call this the centroid C. And when you join the centroid C to each of the vertices, what you get is a collection of triangles. So step one is consider the centroid C. Now if these vertices are V1, V2, V3, and so on, the centroid C is 1 over n times the average of the vertices. It's just the arithmetic mean of the vertices. That will be the point, the centroid of the polygon. It's kind of the center of mass of the polygon. Now this only works for convex regions because the centroid of these vertices here mightn't even be inside the region. It might be outside of the region. It might fall in this bit of the outside here. So this method is only applicable to convex polygons. Then joining all vertices Vj to the centroid C splits R into triangles. So now we can ask ourselves a simpler problem. Now we can solve the general problem of is X inside this convex polygon by just testing each of the triangles and finding out is X inside any of those triangles. Test each triangle for inclusion of X. So how do we solve this simpler problem? Here's a triangle. Here's X. Or maybe here's another candidate for X. How is the computer going to know whether X is outside the triangle or inside the triangle? The computer can't draw it and look well. Sophisticated software with computer vision could look at the picture with a camera, I guess, but that's not. We're thinking it's just from the numerical data of the vertices, the position of the coordinates. How can the computer decide whether this X is inside the triangle or outside it? Test each triangle for inclusion of X. Well, let me label the vertices of our triangle. So a triangle only has three vertices, V1, V2, and V3. And the procedure here is to test each condition. Test each of three conditions. The first one is the question, is X on the same side of the edge V1, V2 as V3? So we look at X and we ask, is it on the same side of the edge V1, V2 as the other vertex V3? And you just repeat this test for each of the three sides. So is X on the same side of V2, V3 as V1? Question mark. And 3 is X, so just the last test is X on the same side of V3, V1 as 2. Now you can see for this point X inside the triangle, the answer to each of those three questions is yes. For that X inside the triangle. But for this X which is outside the triangle, one of those, the answer is no, because this X out here is on the opposite side of V2, V3 compared to V1. V1 and X lie on opposite sides of the edge V2, V3. It's to the same side of V1, V2 as V3, and it's also to the same side of V1, V3 as V2. But this edge here, this point X on the outside of the triangle and this other vertex lie on opposite sides of the edge. So you test each of those three conditions. If yes to all three, then x is inside the triangle. If no to any of them, any of the three, if no to any of the three, x is outside the triangle. But now the question is, how do you test these kind of conditions? How do you know whether two points are on the same side of the line or on opposite sides of the line? How do you test that? You see, we pose the original problem, we keep on replacing the problem by different questions, by more fundamental questions, kind of lower level questions. So now, how do we solve the same side problem? So I'll just simplify. Let's say we've got point A, point B, point X, and point Y. Okay, so here, obviously, X and Y lie on opposite sides of AB. This version of the diagram, we've got A and B. Here, I'm showing X and Y both lie on the same side. So here's a line between points A and B. The first version of the diagram, I've got X and Y on opposite sides of the line. Here's the second version of the diagram with my line A to B. But here now, both of the points X and Y lie above them. What's the difference between these two pictures in a way that the computer can decide? So how do we answer this in a way that comes from the vectors themselves, comes from if we take the vector b minus a, b minus a is the vector which goes along the line from A to B. And we also take this other vector here, which goes from A to X. So this b minus a here is the vector that goes from A to B. And if we take the vector x minus a, this is the vector that goes from A to X. What we do is we consider the vector cross product. The vector cross product is a vector which comes off the plane of the page. And, well, oh my gosh, I don't know if I can remember this. It goes by a right-hand rule. So this cross product, well, it's either coming off the page directly at you or it's coming off the page into the wall, away from you. It's going one of those two ways. But because so this would call normal 1. Normal 2 will be b minus a cross product with y minus a. That we'll call normal 2. Now, if x and y lie on opposite sides of the line, these two normals will be coming off the plane in opposite directions. One will be coming towards you, the other one will be going into the wall. And this finally can be detected by the computer If the computer has the coefficients of a, b, x, and y, it can work out coefficients of the cross products. And it can now do a dot product between them. And the condition it searches here for is a negative dot product. Two vectors going in exactly opposite directions have a negative dot product because the angle between them is pi radians, 180 degrees. The cosine of pi radians is -1. The cosine of the angle between the two vectors is what gives the dot product its positive or negative sign. Whereas on the other side of the diagram, the other version of this diagram, where I've drawn x and y on the same side, here, again, we define these two normal vectors in exactly the same way, n1 and n2. But here, when we evaluate the dot product n1 dot n2, we'll get a positive dot product. Because these will be two vectors which are going in exactly the same direction. I won't waste time remembering or looking up which one it is, but I think it's a right-handed rule for, well, it's either a right-handed or a left-handed rule. I think it's a right-handed rule for determining the direction of the cross product. Because if it's right-handed, it'll go up that way, and if it's left-handed, it'll go up exactly the same. But the point is, well, when x and y are both to the same side of the line AB, we form these normals like this, then the two normals go in the same direction. So they'll have a positive dot product. Right? So if the original problem is specified in terms of components, those are all available to the computer. The computer can calculate the location of the centroid, which then determines a bunch of triangles, like each pair of neighboring vertices from the boundary of the polygon. You take those two together with the centroid, that determines a triangle. So the computer can go through each of those triangles and test this question. Is x inside the triangle or outside? Does that by testing each of the three sides and asks, is x to the same side of each edge of the triangle as the opposite vertex to that? The answer is yes for all three, as it is for this one inside. The conclusion is the point is inside the triangle. If any of them give a negative answer, which will happen for this x on the outside, it's to the opposite side of V3, V2 as compared to V1. If any of these questions have a negative answer, the point x is outside the triangle. And finally, how does the computer decide this same side problem? It does it by calculating normal vectors and checking the dot product, seeing whether it's a negative answer or a positive answer. So if x is inside any of the triangles, x is within the polygon. But it can determine the answer to that question. But if x is outside all the triangles, then it's outside the polygon. So at least in the case of convex polygons, computer can decide whether or not a given point in the plane is inside or outside a given polygon in the plane. Okay, with this problem, we're still just setting this whole problem within a 2D world. We only, the data that defines that everything just has two components. We've still got a bit of explaining to do to show how this method can be used or we can reduce the problem in 3 dimensions in our virtual environment down to this 2-dimensional problem. But what about, before we get to that, let's tackle the general case. What if my polygon is non-convex? What do you do then? What if my polygon is non-convex? Well, there's 2 possible methods. One method is, here's our badly behaved non-convex polygon. One approach would be to just make use of this triangle approach. Still split it up into triangles in some way. And triangles, of course, are convex. So one approach would be to split it up into convex bits. And one more. Split it up into triangles, decompose into triangles. Some way. Use the previous approach. Test whether the point is in any of the triangles. If it's in any of the triangles, it's inside the polygon. If it's outside all of the triangles, then it's outside the polygon. But there's a quite different, or at first glance anyway, quite different way of answering this question, which is quite appealing in its simplicity. So that's one approach, or you can do 2. Well, again, draw my non-convex polygon. So if I point to a point and ask you quickly, like, is this inside or outside? Inside or outside? It's hard to answer. So here's the point we're testing. What have I done there? What I've done there is I've taken an array, and in principle any array will do, more or less, is to take a ray beginning at the point x. So what array is half a line. You know, line is a thing that extends infinitely in both directions, up there and up there. Array is something which has a beginning point and then goes off in some direction. So half a line from x, from the test point to x. So this is the point where we want to know, is this inside or outside? And what we do is we look for intersections of the ray with edges of the polygon. So you find, but more importantly, count intersections of the ray with edges of the polygon. The computer can certainly do that. I mean, the computer has all the information of the vertices of the polygon in order, so it can find, it can construct all the edges of the polygon, joining the straight line, joining one vertex to the following vertex. The computer is given the coordinates at the starting point x. The computer can supply a direction for the ray. We can just come straight down the page. And then it's just the problem of finding these intersections is just the problem of solving do two lines in 2 dimensions intersect. So there's a ray which has a certain given beginning point and a direction. Does a ray intersect another line in 3 dimensions? So how does the computer know whether it's inside or outside the polygon? Anybody tell me? And I mean, the clue is in the thing here. It's not so much the positions of these intersections that's important, but it's counting. Yeah. So it's to do with the parity of this number. If you're in, if the parity is one way, you're one way. It's one conclusion. If it's the other way, it's the opposite conclusion. Figure out what it is. Well, consider certainly far, far away from the polygon, you're outside the polygon. Yeah? Polygon is a finite structure, so it's contained within a finite region of the plane. So far away from the polygon is outside the polygon. So as you move along the ray back towards x, the first time you intersect one of the sides, you move from outside to inside the polygon. So that first intersection brings you inside. But when you go through another intersection, that brings you outside. But then if there's another intersection, that must bring you inside again. But then if you cross the boundary again, you're outside. If you cross it again, you're inside. So this x is inside the polygon because there's a 1, 2, 3, 4, 5, 6 is an even number of intersections of this ray with polygon edges. So even number odd number. There's even number of regions we step through. But look, there's 1, 2, 3, 4, 5. Odd number of intersections. So odd number of intersections brings you inside the polygon because you begin far away outside. You go through an odd number of transitions. You move from the outside to the inside. Whereas if it's an even number of transitions, you go from the outside, but you do an even number. Each transition is split to be from the outside to the inside. So if it's an even number, you remain outside. Okay. So if it's an odd number of intersections, implies x is inside R. Inside the polygon R. If it's an even number, x is outside R. So this is quite appealing. It's I think it's simpler and more direct than the triangle approach before. But the triangle approach has things to recommend it as well. Especially since, actual computer graphics implementations quite often assemble every object in the virtual world out of only triangles or only polygons with a certain number of fixed edges. Because it can handle thousands or millions of those and make them really small, that can build up very detailed picture. But this one, taking the half line or the ray from the test point in a certain direction, testing for intersections of that ray with the edges of the polygons, which is a basic problem of testing intersections of two lines, one of the first problems we solved, and just counting those total number of intersections, that can determine whether the original point is inside or outside the polygons. Is there any questions? Now, the assignment isn't going to involve you implementing one of these approaches. The assignment is going to involve you doing implementing the reduction from a three-dimensional problem to one of these two-dimensional problems. Okay, because already within MATLAB, there's a nice function called inpolygon. Here's the manual entry for it. Inpolygon takes four arguments: xq, yq, xb, and yb. It explains what they are in the help screen, but xq and yq are the x and y coordinates of the point you're querying, the point you're testing, whether it's inside the polygon or outside. xb is a vector listing the x coordinates of the vertices. yv is a vector listing the y coordinates of the vertices. And this function in polygon will return true or false, 0 or 1, 0 for false, 1 for 1, but it's a logical value that it returns, gives you as the output, and it will return true if the point x is inside the polygon, and false if the point is outside. So this is the function that you're going to make use of in assignment 6. But see, this requires two-dimensional information, just x and y coordinates of the test point and the vertices for the polygon. So the task that I want you to solve and to implement into MATLAB for assignment 6 is the reduction problem. And I'm going to describe how you do it. So it's mostly a matter of just filling in the fine details and implementing it into MATLAB. So this is reducing the 3D problem to 2 dimensions in order to use MATLAB's inpolygon function. Inpolygon will do the testing, return true or false, but we need to supply it with an x and y coordinates for the test point and x and y coordinates for the points around the boundary of the polygon. But you see, in our environment is a three-dimensional thing. So everything is specified with three-dimensional vectors. So how to solve this? Now, I'll just let's say show a pentagonal polygon. So a polygon with 5 edges. So this could be the face of one of my buildings in a three-dimensional environment. Okay? I've been calling it R up to now, so I may as well still keep calling it R. Okay? So I've got a polygon R contained in R3, 3 dimensions. So let P denote the plane of R. So P is this infinite plane, extended plane in 3 dimensions, which is defined by R. Now, R, as we've been saying, R is defined by a list, an ordered list of the vertices around the boundary of R. V1, V2, V3, as you traverse the boundary. Now, when I described it first on the first sheet, remember I telling you that we solved the intersection problem of a line with the plane. In the skeleton code I'm going to show you, our line comes specified as a point of origin and a direction vector. Now, we've already discussed and solved how to solve the intersection problem of a line with a plane within 3 dimensions. Now, our plane needed to be referred to with 2 pieces of information: an n, a normal vector for the plane, and q, a reference point within the plane. Now, how do I obtain n and q from the data that I already have? Well, the data I already have are the vectors for the vertices of the polygon, the data that's in the computer's graph. So can I construct n and q from a collection of vertices of a polygon within the plane? Yeah, I can get n. For a start, I can take q just to be one of these vertices. So why not take q to just simply be v1? How can what should I take from my n, my normal vector? Can I construct or magic up a normal vector for this plane from the data? The data is in red. Data is the v1, the v2, the v3. To get a normal vector to the plane, just need 2 vectors lying within the plane. So if I could take the vectors which represent the displacement vectors, or the vectors pointing along 2 of the edges. So I could take v2 minus v1 and v3 minus v1. Those are 2 different vectors within the plane, and I could take their cross product. v2 minus v1, v3 minus v1 are 2 vectors lying within this plane P, and when I take their cross product, then I've got myself a normal vector to the plane. So then I can obtain the point x, which is the intersection, call that line L, the intersection of L with P. Left it a bit ambiguous there, whether that line is going to hit the plane. Is it going to hit it inside the polygon or outside the polygon? That's the question. This L here is going to come along and hit the plane somewhere. This is going to be inside the polygon or outside. Well, you can obtain once you've solved this problem, okay, which we did with basic vectors inside 3 dimensions. We did it in the early weeks of this course. Then we'll have a vector x, vectors v1, v2 to vn, defining the polygon. But we'll have these as 3D vectors. Remember, they all lie in the plane P. So how to convert this to just 2D information which we can then pass to the inpolygon function of MATLAB. How to do that? We've got too many components. The inpolygon function only wants you to give it x and y components. But everything we have, our point of intersection with the line in the plane, our point x, and our vertices, our position vectors of our vertices of the polygon, they all have 3 coordinates. They all have x, y, and z coordinates. Well, this shows an application of some of the things you've been doing in mathematics as well. The process will be to find a basis, find a 2D basis, a two-dimensional basis for the plane P. Because all these things, x, v1 to vn, they're all three-dimensional vectors, but they are all living inside this plane. So if we just could only consider the two-dimensional subspace of the two-dimensional vector space, which is the plane, and then just express everything as vectors in that vector space, two-dimensional, then we have two-dimensional stuff, x and y coordinates, which we could cast in polygon fashion. So find a 2D basis for plane P and express x, v1, v2, etc., vn in terms of this basis. That will give us two-dimensional information, x and y information, which we can then pass to in polygon. So can anybody see a candidate for a basis of the plane P? And we want it to be quite a nice basis, one that we can use to easily get coordinates or components for x and all the v's from that basis. Well, we've already kind of suggested it up here, where here we formed these two vectors, one which goes v1 to v2, and the other one which goes v1 to v3. Those were two vectors lying along the plane, and I cross-producted them to get the normal vector. Well, we can use that kind of idea to get our basis as well. So, solution to this problem. So originally, at the start, we'll set v1 to be this vector v2 minus v1. And v2, we'll set it to be v3 minus v1. So I just want two vectors lying along the plane. So now v1 and v2 generate the plane P. Any vector lying along the plane P could be written as a linear combination of v1 and v2. v1 and v2 are two different vectors lying in the plane P that generate. And in fact, they are a basis for it. Assuming that v2 and v3 are different vectors, they will be linearly independent. But I want them to be a nice standard basis. Okay? I want v1 and v2 to be standard basis, i.e. both unit vectors and perpendicular. That will make it easy to extract components for it. Well, that can be done easily. So I'll take my first vector, E1, to be E1 hat, the unit vector, E1 hat, which is 1 over the norm of B1 1 over the norm of B1 times B1 gives you a unit vector of the direction. Let's call that E1 hat, unit vector E1 hat. E2, I can make a vector E2 which is perpendicular to B1 by taking that to be vector B2, but subtracting from it the component of B2 that's in the direction E1 hat times E1. So my vector B2. So I have my first vector B1. I lengthen that or shrink it appropriately to make it have length 1, to make the unit vector. Then I've got my other vector B2, which is probably not at a right angle to B1, but I want it to be. Well, this construction here, where I subtract from B2 the component of B2 that's in the direction E1, and I subtract that multiple of E1, what that does the job is it takes vector B2 and it straightens it so that I do have a right angle. I remove whatever component of B2 is in the direction E1. So this, my vector here, my pen going upwards, has a little bit of a component, this much along here, in the direction of my first pen. So what I do is I get rid of it, I subtract it, and that straightens it out so that it's now at a right angle to my first pen. Or if my second pen was over there, so there's an acute angle between the two. My upper pen here is quite a large component in the direction of my first pen, my bottom pen. This construction here removes that component. It makes its direction be at a right angle to the first pen. Now this gives me a vector E2. This satisfies E2 is perpendicular to E1 hat, but E2 is probably not a unit vector. So I now set E2 hat to be 1 over the norm of E2 times vector E2. So I make it into a unit vector. So I then have, now we have a nice basis. Now the technical term for nice here is orthonormal. Stephen will be talking about that term a fair bit. Yeah?
Is that B2 multiplied by E1?
Here, B2 dot product with E1. Can't multiply two vectors. Yeah? So this is the dot product of B2 with E1 hat. It's the component of B2 in the direction E1.
Thank you.
So multiply that E1 and subtract. So we now have a nice, the technical term is orthonormal. They're perpendicular vectors and they're both normal. They're both of length 1, both normalized. We have a nice basis of E1 hat and E2 hat for the plane P. They generate the plane. They're at right angles. If you wanted, you could just add in here just a little sketch. You've got E2 hat going up this way, E1 hat coming down here, and there's a nice right angle between them. There are two vectors lying along the plane. So this will be my basis for P. It's just two vectors that generate the whole of P. At the moment, my data for P, the data I'm holding for the problem at the moment is x, v1, v2 up to vn. Those are all three-dimensional vectors. But they're all lying within the plane P. But I can get components of these. Now get components, x and y components, just two-dimensional components, for the three-dimensional vectors x, v1, up to vn. Get components for these in terms of E1 hat and E2 hat. So what do I call it? Yeah, so I'll say vector x is x and y, where component x is vector x dot E1 hat. Component y is vector x dot E2 hat. And so on. Vector v1, I'm going to represent, maybe I should write equal signs here. Vector x is a three-dimensional vector.
That be exams of E1 hat and 2 hat?
Yeah, oh yeah. Two halves. Yeah. Here's some. So vector 1, we'll call this x1, y1. And x1 here is vector v1 dot v1 hat, because this is the component of v1 that goes in the e1 direction, and y1 can be the component of v1 in the e2 direction. And it's within that plane, so those components fully determine the vector v. But you see here, I'm getting a representation for these. Keep going for v2, v3, and so on. We're getting two-dimensionalized the problem. We reduced three-dimensional problem into 2 dimensions, and then that MATLAB's in polygon function is ready and waiting there to accept this 2-dimensional information to return true or false for us, which will tell us whether the point of intersection here, let's just draw it in to complete the picture. So we're showing it here that it actually missed the polygon. There's your vector x somewhere in the plane. This procedure here 2-dimensionalizes all the information. You then pass it in polygon. In polygon tells you whether this x is outside the bar or inside. So then pass this information in the appropriate way. Pass this info to MATLAB's in polygon function. I know we've been talking for an hour and 20 minutes, but I think what I'll do is I'll just keep talking for 5 or 8 minutes more to show you the skeleton code, show you how I want the program to work. I'll give you a handout. Should I do that? Should we take a break now and bring everybody back, or should I talk for 10 more minutes and then we'll break, and I'll only bring you back for queries and questions. So if you really want to, you can go, but I'll be available here if anybody, as long as they want to, until 5. So quick vote for pushing on through or stopping now and take a break. Okay. So pushing on through. Okay, so everybody wants to push on through. Okay, let's push on through. So I've got here a printout now, a bit large. Oh my goodness. There's a lot of stuff here, but I'll talk you through it and I'll direct you to the bits of it that you need to deal with. Okay, so what you've got there is a printout of the skeleton code. So you'll be able to make a few notes on it now, and it's just good to have it. So I'll talk you through that in a moment, but first I'll just run you, so this is my solved version of the problem, just to show you the kind of behavior that we're looking for. Now practically all of this is set up in the skeleton code already. So here's my very minimal village. Okay, I'd like yours to be a little bit more, have a little bit more going on in it. It should have a street of buildings in it. Actually, here I'm going to build the street, actually. So this is I've just got 5 buildings there to begin with, and then I click a start point for the street, and I click a direction for the street, so I get MATLAB to build me a little street of buildings. And now it's asking me to click to define the ray origin. So this is where the laser is going to be shot from. So let's say, now let's clearly hit one of the buildings. So I'm going to shoot from down here. I'm going to go up here. So I've shot from the red circle to the black circle. So I should impact this near side face of that square building. We're looking down on top of the village here. So I should be hitting this side face of that square building. Now then, this is also going to do the animation, the orbiting animation. So to set up the orbiting animation, I want to click to define the center of the orbit, and then click one point which is out on the orbital circle. So I'll click a point. Now, we don't remember the way we did the perspective projection, we assumed everything was the other side of the projection plane. So I don't want to choose a small circle here within the village, because then I'll have some things behind and in front of the projection plane. Because we haven't dealt with the ordering algorithm to delete things that we shouldn't be seeing, everything will get projected to the projector plane. So the things that will be behind me will be upside down and so on. So it'll all get a bit messy. So I'll choose a large enough orbital circle. So this red circle is the center of the orbit. Choose a large enough orbital circle to be completely outside the village. So what the code now, it's running quite slow here. So I'm using MATLAB through the virtualization through the browser, so it's not running very fast. But it's fast enough to get a sense of it. So we're orbiting around the village, we're flying around the village, and for each frame it's calculating the perspective view. So it's separately aligning the environment and perspective projecting the environment for each one of these little frames. You can see here, yeah, indeed, that near side face of that square building has been colored in red. It detected, the code detected that that was the face of the building that was hit by the red. Okay? So it's colored that one in red so that we can see it. Okay? That's roughly how the solution program should operate. To close this window. Now, but what I'm providing you with is the skeleton code, which I'll show you now how the skeleton code runs. So I'll switch to skeleton. This will do all those steps. It'll do all of them except the coloring in. So it still builds my street with a couple of mouse clicks. We can define the ray origin, and define the center of orbit and the orbit radius, and the skeleton code will produce this orbiting view of the environment. We can see there that, well, you can kind of see that no building has been colored in. It hasn't done the detection of which face of the building the ray hit. Okay? Okay, so we'll turn to your handout now, which is a printout of the skeleton code. It's a little bit large, 500 odd lines in it, and it's based on the skeleton code for assignment 5. Now there's lots of comments in the code that explain things, but first I just want to draw your attention to line 240. So it's on page well, it's on page 5 of everybody's handout. Not in yours for seeing, but if you go to code line 240. The code lines are printed down the left. So if you go to line 240. Now here in the program is where the code starts to do the detection of which face of the building is hit. Now the mouse clicks that you do on the plan view, they feed into these two variables up here at line 237. You've got ray direction and ray origin. Okay, so ray origin is the point from which the ray is fired, and ray direction is a direction vector going in the direction of the ray. What the code is going to build up is, on line 243 here, we initialize an empty vector called intersection pairs. And you can see from the comments there, on line 240, intersection pairs matrix will have rows Ti. And this is indicating that the ith polygon is struck by the ray at time t. So for example, if this array intersection pairs, if it held the row 12.23, that would indicate that the third polygon in the environment was struck by the ray at time value 12.2. Clearly, the ray that you shoot through the village could intersect many polygons. It could go through the buildings and intersect many of the polygons. We're looking for the first one hit by the ray. So what we're going to do, you see here down line 249, line 249 is a for loop. And it goes from 1 to n polys. N polys is the total number of polygons in the environment. And it tests each polygon for whether the ray intersects the plane containing that polygon and whether that intersection point is within the polygon or not. So this command here, at line 257, there's two functions I want to draw your attention to here. At line 257, we've got this function, line plane intersection. So it does what it says on the tin. It tests a line and a plane in the three-dimensional environment, and it returns the intersection data. The time of intersection, t, and the point of intersection. And what information do you have to feed that function? You have to feed it the ray origin, the ray direction, polyverts :1, which is a reference point in the polygon. But that's built into the skeleton code. And normal is a normal vector for the polygon, for the plane containing the polygon. But again, that is constructed for you in the skeleton code here. So this line 257, returns a time value and a point. The time value when the intersection occurs, and point is a vector in the 3D environment, which is the point of intersection of the line with the plane. Now, we then have to test, is that point of intersection within the polygon? We only do it if the time value is positive. Remember, we can get negative intersections happening in negative time. That's intersections backwards from the ray origin, which we don't treat. We'll just discard that information. So this next test is only carried out if the time value is non-negative, and so this double ampersand on line 261, this is the conjunction, the and of these two conditions. Then we're calling the second function. I want to draw your attention. This is point in polygon interior. This is going to be your function you're going to write. This function tests whether the point represented here is the variable point. This is the point of intersection of the line with the plane, whether it is inside the ith polygon. This I number is an index number, the index number for the ith polygon. I is the loop variable. See, this is all inside this for loop, beginning on line 249. For I equals 1, up to the number of polygons. So I is going through polygon 1, polygon 2, polygon 3, polygon 4, etc. For each polygon, it's obtaining the intersection between the line from the ray origin in the ray direction, in the intersection of that with the plane of the ith polygon, and if the time is positive, testing for whether it's inside or outside the ith polygon. So point in polygon interior, that function there is used in the condition for this if statement. So if the time is positive and the point is in the polygon interior, this function has to return a truth value. Point in polygon function, which I'll focus you on in a moment, that's going to return a truth value, true or false. If the time is positive and the point is within the polygon, this function returns true, then this line, intersection pairs equals intersection pairs along with an extra row ti. We add on the row t, which is the time value of the intersection, and I, which is the index of the ith polygon. We add that to the array intersection pairs if the point of intersection is in the polygon interior. That's the effect of this if loop here. If the time is positive and the point is within the polygon interior, that pair, t and I, will be added on as an extra row onto the intersection pairs array. Then the skeleton code takes over, and we'll do all the rest. This next line in 267, this command redefines intersection pairs as sort rows intersection pairs. That's going to sort all those intersection pairs according to the timestamp. So we put the earliest one first. That will be the one that actually gets hit by the ray. That's the one that the code will color red. All the rest of the code there, you can read the comments to follow what it does, but it's already in place and we'll take over and complete the job. So what you have to focus on for this assignment is these two functions. On line 257, the line plane intersection function, and on line 261, the point in polygon interior function. Now these are functions which are defined below. Here we're still within the main script, the top function in this end file. So if I take you down to line plane intersection, which is on 534, if you look down to line 534, this function is rather empty at the moment. This is what you have to fill in. Okay? There's a big comment here describing what this function should do. You can tell by the declaration on line 534, it says function t point equals line plane intersection PDQN. So t and point are the outputs of the function. Time the intersection happens. Point is the point of intersection. And the inputs are PDQN. P is the origin of the line. B is the direction vector of the line. Q, the reference point to the plane. N, the normal vector to the plane. Okay, that's all contained in the comment. Now, if there is no intersection, the one case where there aren't any intersections is if the direction vector V is parallel to the plane. Then I've asked you to arrange it so that the function returns a t value of -1. And in fact, in the skeleton form, that's the value that it returns at the moment. It just sets t equal to -1. Negative t values will be discarded. Remember the if statement we looked at. If the time was positive and the point was in the polygon interior, then we added the intersection pair. But if we see a negative time, we'll just discard it and forget about it. It's not a genuine intersection. So if there isn't any intersection, we should return a negative value of t. And we may find a negative value of t as well. So you need to put in the code here to figure out what the correct value of t is. What's the time at which that line intersects the plane? I've already filled in the point line. The intersection point should be p plus tv. Once t has its correct value, p plus tv will be the point along that line at time t. That will be the intersection. So you look at the early material we looked at for vector intersection problems in 3 dimensions, and we've already described how to find the intersection of a line with a plane. So you have to complete that function there. Line plane intersection of 5, 3, 4. Then right after it, beginning on 5, 5, 3, right at the bottom of the code is the function point in polygon interior. So as it currently stands, this function returns false for all inputs. Because look, I've defined the output variable in interior to be 0. You will need to provide an implementation of the method described in class, that method we just went through, where we constructed a pair of basis vectors for the plane out of edges of the polygon. Then we two-dimensionalized everything. So you want to implement that procedure. We described it in a fair amount of detail. Implement that procedure here, and then you'll make a call to the inpolygon function. So inpolygon is a built-in function into MATLAB already. Look up the help on it, which I showed you, a while ago in this class. It tells you what order the inputs should be, and the function inpolygon will return a truth value, true or false. And you just store that in this variable. Have that be the last statement in this function. So in interior equals in polygon, and then you're passing the appropriate inputs into the function in polygon. Now you see there's some structure in that statement there, global polyverts. When you read all the comments in the code, verts is a global variable, meaning it's accessible to all the functions in this M file. Verts is holding all of the vertices of your three-dimensional environment. Okay? Position vector of every single vertex of every building in your environment. And poly is a big array holding all the polygons. The polygons are stored as sequences of vertex labels. Each vertex has a label, it's positioned in the verts array. The first vertex, the second vertex, the third vertex, whatever in your environment. And the polygons in your environment are specified as sequences of vertex labels. So your function may need to call on, may need to access the data in poly and verts. And the I that you're passing into this function, this point in polygon interior function, I is the index of the ith polygon. Okay, that's described. The point is this point of intersection. Okay, so that's what you have to do. So in short, you just need to complete those final two functions, line plane intersection and point in polygon interior. The skeleton code does everything else for you. So that skeleton code I'll upload to the normal position in Moodle. It's not up there at the moment, I'll upload it after class. And you'll find it beside the assignment submission link for this assignment. Okay, well, we'll have a break now. Anybody that remains, I'm willing to stay here up to 5. But I can answer any queries you have. I can look at any of the work you're doing on the assignments and give you any feedback if you like. But I'll leave it up to you whether you remain.